My name is Sudheer. I'm joined here by Warda. We work in the pricing and data science team at QBE. I'm going to talk to you a little bit about managing portfolio climate risk at scale and in the insurance industry. Just a brief agenda. I'm going to give you quite a brief introduction to insurance and what we do within the pricing team, how we use spatial data science at QBE, and Warda is going to give you a little walkthrough of a case study where we use some geospatial data to look at some hurricane and portfolio risks. So who are we at QBE? QBE, we are a commercial insurer, so we're quite different from a personal lines insurer. We insure things like fleets of marine ships, we insure political violence, we insure portfolios of property. So we do quite specialist insurance, and we're quite broad, and we have a global reach across the world. The company's kind of goal is to emphasize risk management, and that means like offering risk assessments, managing your claims when you have a claim, all of these kind of things. So how does the pricing and data science team tie into what QBE does? So we price the risk. So what do we do when we typically price a risk? So I'm sure most of you might have heard what an actuary is. Our team is a hybrid of pricing and data science and actuarial. So a typical actuarial model revolves around kind of three components. First component is kind of the frequency component. So when we model like a historical portfolio, we'll be looking at the frequency of claims. So the frequency models are typically represented by a Poisson distribution. Then we look at the severity component, which is essentially how expensive claims are. That is typically represented by gamma distribution. You can also model the two things together, and those modeling them together is typically represented by a Tweedy distribution. But with an actuarial model, you would be typically looking at historical data. So how do we actually price climate risk? So within our company, we have an entire team of people, which is called the catastrophe modeling team. And they use a stochastic model, so you can't use historical data to price climate-related risk. Because if you never experienced a hurricane in a particular region, doesn't mean that the hurricane is not going to hit in that region. So what is a CAT model? It's a stochastic model. It's a computerized system with kind of a set of simulated events going back in time. So some of it's based off of real events, some of it's kind of based off simulated events. We run the kind of simulations against a set of locations, a set of assets. Then we apply kind of the insurance structures on top of it, and then we get essentially an insurable loss attached to each of the assets. As you can kind of see in the icons at the bottom, we are exposed to kind of a ton of different climate perils, everything from wildfire to earthquake to volcanic activity to convective storm. So the objective with kind of climate-related pricing is to kind of estimate what our average expected loss is from a climate risk is every year, versus the actuarial thing, which is to kind of cover your expected losses but remain competitive in the market. So how does geospatial data help with the pricing process? There's kind of a few different components that we would use. Regionalization, kind of identifying areas where we might want to expand kind of our like similar characteristics in terms of hazard, in terms of kind of like the market, kind of market rates and things like that. Risk selection, can we identify any characteristics of a particular asset that makes it more suitable for underwriting? Exclusionary criteria, can we identify areas that we just don't want to write insurance? Event response analysis, that's kind of your typical bread and butter use case where we would look at kind of post-event map to see which of our assets are kind of impacted. Accumulation management, do we have any clusters of kind of too much risk in a particular area where if a hurricane came through, we would put ourselves in financial jeopardy. Visualization, climate trends, these are kind of expected use cases. So we have quite a few different geospatial data sources, everything from marine telematics to kind of Google Earth Engine. But how do we actually process that data within our team? We're quite a heavy Python shop. We kind of rely on your typical bread and butter geospatial libraries. That's H3. I think everyone here knows what H3 is. but there's a library we've been playing with recently, which is called H3RonPy, which allows you to kind of vectorize and transform raster data into H3 quite quickly. We use a combination of kind of cloud databases with serverless functions as well as cloud compute, but that's kind of the general kind of core stack that we're using. So I'm going to pass it on to Warda, who's going to tell you a little bit more about how we actually used it in our case study.
Thank you very much, Sudheer, and good morning, everyone. Like Sudheer mentioned, geographical data sets are of immense importance within the insurance sector. Shown here are two examples. So the first one, where we are using the location level information to understand the dispersion of accounts within a certain portfolio. So we can use this information to identify hotspots, by which I mean regions where we are writing most of our exposure, and then put in some strategy to mitigate that risk. The second example shows custom hazard maps. So we can create custom hazard maps for certain types of risk to better understand the risk distribution, and then to put in steps to manage that risk in a better way. Next, I'm going to walk through one of the case studies. So we use location level information here to compare the performance of accounts within a portfolio. So the portfolio that we focused on here was property. So we can do it for any line of business. And we are looking at their performance during different hurricanes. So the idea is to try to understand that if two accounts experienced a hurricane of a very similar strength, do their performance match? And if not, try to understand those differences. So we made use of 3 different data sets here. The first one was Google Earth Engine. Eric touched on that in his presentation. So Google Earth Engine hosts petabyte of data. It includes satellite imagery as well as geographical data sets. So the two image collections that we used are shown here at the bottom. So the first one gave us wind speed information, and the second one included an hourly analysis of snow and rainfall taken at 3-hour intervals using a satellite mission. And the first one, sorry, I didn't talk about the first one. So the first one is just an hourly analysis of the weather conditions near the Earth's surface. Now, if you look at these image collections, they are from a certain time period. So the first one is from 2011 to 2022, and the second one from 2000 to 2022. But each hurricane would have occurred during a very specific period. So what we would do is reduce these images, which are just a stack of images being reduced to a certain time period to correspond to that hurricane period. And then that would be used to obtain the hurricane footprint. I'll come to that in the next slide. So once we have got our hurricane footprints, we want to find the exposure within that footprint. That's where the second data set comes. And the exposure is what's the value of the risk that we are writing. And then the final data set is the claims, so that means the losses incurred. But the claims data that we have within the company lacks location level information, so to join it back onto the exposure data, we just used a key, and that key is just the policy reference concatenated with the accident year. And I forgot to mention a very important point, that to assess this importance, we are using a metric called damage factor. So damage factor is just the losses that occurred over the exposure or the value of the risk that we are writing. So I'll talk a bit more about these hurricane footprints. So I talked about the temporal reduction, that how we are going to reduce them over time to get a single image for each hurricane, but how we are going to get a value for each region. So for that, we are going to use the H3 library, which most of you would be familiar with. So Uber has basically hexified the entire globe, and we have these hexes available from resolution 1 to 16. If we go to any finer resolution, we are going to get to smaller and smaller hexagons. For this specific case study, we used a resolution of 6, because going to anything finer than that would have been computationally very expensive. So we hexified the entire US region, and then we used the images, which I talked about in the previous slide, to get a single value over each one of those hexagons. So for example, if you're using the first image, we are going to spatially reduce that image over these hexagons so that we get a single wind speed value for each one of them. And then the final step was just binning these hexagons which now have the wind speed values attached with them. And for this, we use the Saffir-Simpson scale. So anything below 17 meter per second is going to be depression. Above that, we have storm, and anything above 33 is going to be GAD. So using these three different categories, we binned the wind speed data and then colored the hexagons using that color coding. That's shown here in this slide. And also, in addition, I'm showing the hurricane tracks, which we obtained from a public data set present within GCP BigQuery. So the idea is just to show that the regions which were hit by strong wind speed are indirect part of these hurricane tracks. So this allowed us to obtain the hurricane footprints for 12 different hurricanes. And then the next step was getting the exposure within that and then getting the losses within those regions. And particularly, we focused on the tail regions here because we want to focus on the areas which were hit by strong wind speed, using the assumption here that if an area is hit by a strong wind speed, it suffered a hurricane of more strength and would have incurred more losses. And the final slide here, so after we have got these losses, we have a wind speed value for each one of the locations. If we look at the cumulative losses against the wind speed bins, we can see that there is a direct correlation there. And that's why we decided to use as one of our features, and we trained a model, which was a simple 3D model with a linear objective, along with some other features, because we are focusing on the property portfolio here. So the other features were construction groups and occupancy types. And the modeling results are shown on the left. So we have got the benchmark damage factor, the benchmark wind speed, along with the average ones. So the idea is to use them to compare the performance of accounts or portfolios against each other, provided very similar wind speed conditions. And also we can compare the damage factors against one another for different accounts. For example, if we just look at the benchmark wind speed and benchmark damage factor, the first thing we see is that it follows the trend nicely. Just in cases or hurricanes, it's not following the trend. It's because of some post-hurricane event, like a flood, which was mainly responsible for the losses, as opposed to the hurricane being responsible for that. And if we just pick an individual account, and just to point out, these numbers are just for reference. And if we pick just an individual account and see how that wind speed relates to the benchmark wind speed, and if we notice that the wind speed is higher than the benchmark, we would expect its damage factor to be higher. So the next step would be comparing its damage factor with the benchmark damage factor. And if we see that it's higher, all good. But if not, we have to understand that discrepancy, that what's going wrong there. So thank you very much for your attention. I think I finished before time, but it's okay.